You hear quantum computing and you think future. You think cracking codes, designing drugs, predicting weather 1,000 years out. But almost nobody talks about the machines themselves. Almost nobody knows there are 7 radically different ways to build one, 7 paths to the same impossible goal. Superconducting circuits chilled to 15 thousandths of a degree above absolute zero, atoms trapped in laser light. Photons bouncing through silicon chips at room temperature. Ions levitated in electromagnetic fields with 99.9% accuracy. Quantum dots smaller than viruses. Topological qubits that Microsoft spent 20 years chasing. Anilers optimizing truck routes in minutes that would take supercomputers a million years. Which one wins? Which one changes everything? What happens when they scale to a million qubits? Let's go back. May 1981. Endicott House in Dedham, Massachusetts. MIT hosts a conference on the physics of computation with IBM. Richard Feynman steps to the podium and drops a grenade. Classical computers can't simulate nature, he says, because nature is quantum. You need a quantum machine to simulate quantum systems. He introduces superposition, entanglement, the idea that bits could be 0 and 1 at the same time. This wasn't philosophy, it was physics, the foundation for everything that followed. If you value documented quantum computing history and breakthrough engineering like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual using sources from Nature Journal published February 2025, showing Microsoft's Majorana 1 processor. Science Journal published March 12, 2025, confirming D-Wave's quantum supremacy on magnetic materials simulation. And MIT Technology Review published November 5, 2025, detailing Quantinuum's Helios system specifications. These are peer-reviewed primary sources, not tech blogs. Now back to the information. Fast forward to today. The United Nations declared 2025 the International Year of Quantum Science and Technology. 100 years since quantum mechanics. McKinsey published their 4th annual Quantum Technology Monitor in June 2025. The quantum computing industry generated $650 million to $750 million in revenue in 2024, and they're projecting over $1 billion in 2025. Investment in 2024 totaled about $1.4 billion concentrated in late-stage companies. 2 startups received half the money. PsiQuantum got $300 million. Quantinuum pulled in another $300 million. Australia committed $620 million to build the world's first utility-scale fault-tolerant quantum computer in Brisbane. Illinois announced a $500 million quantum park. Singapore invested $222 million. Japan committed $7.4 billion in early 2025. This isn't speculation money anymore. This is infrastructure. The race splits 7 ways. Each technology uses quantum mechanics but builds qubits differently. Each has advantages, each has problems. Number 1, superconducting qubits, the most commercialized approach, IBM, Google, Rigetti. These machines use superconducting circuits as qubits, made from materials that conduct electricity with 0 resistance at temperatures near absolute zero. 15 millikelvin, that's 15 thousandths of a degree above absolute zero. Negative 459.65 Fahrenheit. Inside a dilution refrigerator that costs hundreds of thousands of dollars and requires liquid helium. The circuits are fabricated on silicon chips using processes adapted from the semiconductor industry. Each qubit is a Josephson junction, a thin insulating barrier between 2 superconductors. Apply voltage and the supercurrent creates quantum states. Superposition, entanglement, spin Q published an analysis in February 2025 breaking down the technology. Superconducting qubits scale easily onto chips. IBM's Condor processor announced in 2023 has 1,121 qubits arranged in a honeycomb pattern. First quantum processor to break 1,000 qubits. Google's Sycamore chip with 53 qubits demonstrated quantum supremacy in 2019, completing a calculation in 200 seconds that would take the world's fastest supercomputer 10,000 years. Google announced their Willow chip in December 2024, showing breakthroughs in quantum error correction, reducing errors as you add more qubits. For decades, that was backwards. More qubits meant more errors. Willow flipped it. But there are trade-offs. Low temperature requirements, complex dilution refrigerators, quantum noise. Despite advances, superconducting qubits are vulnerable to environmental interference, causing computation errors. Interqubit interactions become increasingly complex as you add more qubits. IBM released their quantum roadmap through 2033 and 2025. They're targeting a quantum-centric supercomputer by 2025 with over 4,000 qubits. Their Heron processor is already demonstrating progress. They aim for utility-scale workloads, leveraging modular architectures like IBM Quantum System 2, supporting up to 16,632 qubits. The focus is improving circuit quality to run 5,000 gates with parametric circuits. They're working on quantum error correction and middleware automation. CEO Arvind Krishna predicts quantum computing will be a key differentiator for businesses, enabling new algorithms for optimization and simulation. Researchers at IBM see near-term advantages in chemistry and materials science. Rigetti's roadmap, updated in Q3 2024, plans a 36-qubit system by mid-2025 and over 100 qubits by year-end. Long-term goal is a 336-qubit Lyra system. They focus on superconducting qubits and multi-chip architectures, leveraging alternating bias-assisted annealing for precision. They released the Ankaya 3 system, with 84 qubits achieving 99+% 2-qubit gate fidelity by 2024. Their modular approach aims for practical applications in machine learning and optimization. CEO Dr. Subodh Kulkarni said the company will work toward practical uses, adding the remarkable performance of Ankaya. 3 reinforces their leadership in the superconducting quantum computing field, which they believe is the winning modality due to fast gate speeds and well-established manufacturing processes. Number 2, topological qubits, the longest shot, the highest reward. Microsoft bet everything on this. In February 2025, Microsoft unveiled Majorana 1, 8 topological qubits, world's first. Published in Nature February 1925. The chip uses a new class of materials called topoconductors, indium arsenide semiconductor combined with aluminum superconductor. Cool it to near absolute zero. Apply magnetic fields. The material enters a topological superconducting phase. Majorana zero modes emerge at the ends of nanowires. These quasiparticles are their own antiparticles. They were predicted in 1937 by Italian physicist Ettore Majorana. For nearly a century, they existed only in textbooks. Now, Microsoft creates and controls them on demand. Topological qubits promise hardware-level error correction. Information is distributed across the system rather than stored in individual particles, less likely to lose coherence, more fault-tolerant. Majorana 1 has 8 qubits designed to scale to 1 million on a single chip. Microsoft Station Q Director Ketan Nayak, a professor of physics at UC Santa Barbara and technical fellow for quantum hardware at Microsoft, announced it at Station Q's annual conference in Santa Barbara. The chip is a proof of concept. Measurements are digitally controlled instead of analog. That's crucial. Commercially important applications require trillions of operations on 1 million qubits. Fine-tuned analog control of each qubit would be prohibitive. Digital control vastly simplifies how quantum computing works. Microsoft published a roadmap in their preprint showing scaling from single qubit devices to arrays enabling quantum error correction. Building blocks demonstrated. Quantum information encoded in Majorana, 0 modes protected by topology, processed through measurements. They're ready to move from physics breakthrough to practical implementation. DARPA included Microsoft in a program to evaluate whether innovative quantum computing technologies could build commercially relevant quantum systems faster than conventionally believed possible. Microsoft technical fellow Matthias Troyer said from the start they wanted to make a quantum computer for commercial impact, not just thought leadership. They knew they needed a new qubit. They knew they had to scale, but skeptics exist. Nature published a follow-up article, March 18, 2025, titled Microsoft Quantum Computing Claim Still Lacks Evidence. Physicists are dubious. Some attendees at presentations left with questions unanswered. Independent researchers questioned whether the experimental data definitively proves Majorana 0 modes versus alternative explanations. Henrik Legg posted a preprint on R. February 2025, suggesting non-topological systems could mimic the observed signatures. Microsoft responded in July 2025 with additional data published on AR showing distinct parity lifetimes in tetron qubit devices. X-type measurements, 14.5 microseconds. Z-type measurements, 12.4 milliseconds. 3 orders of magnitude difference. The disparity underscores distinct underlying physical processes. Still, researchers acknowledge current experimental configuration does not definitively rule out non-topological explanations. Cornell, IBM Harvard, and Weizmann Institute demonstrated in July 2025 the first error-resistant implementation of universal quantum gates using Fibonacci anyone braiding. Published findings show fault-tolerant behavior critical for scalable quantum computing. They encoded quantum information by braiding exotic quasiparticles in 2 dimensions. applied the approach to chromatic polynomials, a computationally hard problem that grows exponentially beyond classical computers. Nokia Bell Labs, led by principal researcher Robert Willett, expects to hit several key milestones in 2025, showing viability of their topological quantum research. In 2026, they hope to demonstrate a stable topological qubit. Willett said they're building a new type of qubit that is intrinsically stable and easy to control with extremely low error rates, meaning they would not need massive redundancy into quantum computers, making them smaller, more energy efficient, and massively powerful. Number 3, trapped ion qubits. The Precision Machines, Quantinuum, IonQ Alpine, Quantum Technologies, Oxford Ionics. These systems use individual ions, charged atoms suspended in electromagnetic fields as qubits. The ions are manipulated using laser beams to perform quantum operations. Trapped ions offer advantages including low error rates and all-to-all connectivity. Any ion can interact with any other ion in the trap. That's huge for error correction approaches requiring fewer physical qubits. Quantinuum unveiled Helios in November 2025. Third-generation trapped ion quantum computer, 98 barium ions at a time. Previous system H2 used 56 ytterbium qubits. Barium ions proved easier to control than ytterbium. The system features 99.921% 2-qubit gate fidelity and 99.9975% single qubit fidelity, according to company specifications published November 5, 2025. Jennifer Strably, vice president at Quantinuum, said Helios is an important proof point in their roadmap about how they'll scale to larger physical systems. The ions are located on a thumbnail-sized chip cooled to about 15 Kelvin, negative 430, 2.67 Fahrenheit on top of an optical table. Users access the computer by logging in remotely over the cloud. Quantinuum demonstrated error correction on the fly. A new capability for its machines, NVIDIA GPUs were used to identify errors in the qubits in parallel. David Hayes, director of computational theory and design, said it's becoming increasingly apparent how important all-to-all connectivity is for high-performing systems. Unlike superconducting circuits affixed at chip surfaces, ions can be shuffled around. They can interact with every other ion in the computer. Superconducting qubits can only interact with direct neighbors, so computation between non-adjacent qubits requires several intermediate steps involving qubits in between. MIT Technology Review, published November 5, 2025, that it's not clear what type of qubit will win in the long run. Each type has design benefits that could ultimately make it easier to scale. Ions offer an advantage because they produce relatively few errors. Even with fewer physical qubits, you can do more. However, it's easier to manufacture superconducting qubits. Qubits made of neutral atoms are easier to trap than ions. Quantinuum plans to build another version of Helios in Minnesota. They've begun building a prototype for fourth-generation computer, sole planned for 2027, with 192 physical qubits. In 2029, the company hopes to release Apollo with thousands of physical qubits and should be fully fault-tolerant, able to implement error correction at large scale. Quantinuum achieved 56-qubit system, H21 in June 2024. First quantum computer with 56 trapped ion qubits. Joint team from Quantinuum and JP Chase ran a random circuit sampling algorithm, achieving a remarkable 100 times improvement over prior industry results from Google in 2019. Set a new world record for the cross-entropy benchmark. H2's combination of scale and hardware fidelity makes it difficult for today's most powerful supercomputers and other quantum computing architectures to match. CEO Rajiv Hazra said they're extending their lead in the race towards fault-tolerant quantum computing, accelerating research for customers like JP Chase in ways that aren't possible with any other technology. Honeywell completed a $600 million equity funding round for Quantinuum in November 2025 at a pre-money valuation of $10 billion. Investment includes Quanta Computer and Ventures, NVIDIA's venture capital arm QED Investors, JP Chase Mitsui, Amgen Cambridge, Quantum Holdings, Serendipity Capital, and Honeywell. Capital will accelerate hardware and software roadmap, including continued development of fault-tolerant quantum systems and global expansion. Quantinuum expanding global footprint with research and operations centers in Singapore, New Mexico, and Qatar. Collaboration with Singapore's National Quantum Office and National Quantum Computing Hub focuses on computational biology, materials, science, and finance. IonQ unveiled accelerated quantum computing roadmap in June 2025. Maryland-based startup known for trapped ion technology outlined dramatic scaling milestones. By leveraging Oxford Ionics' chip-integrated ion traps and LightSync's photonic interconnects IonQ's recent acquisitions, the company plans to boost qubit counts by orders of magnitude. New timeline projects jump from today's tens of qubits to about 20,000 physical qubits by 2028, spread across 2 entangled chips reaching about 2 million physical qubits by 2030. IonQ estimates this will equate to about 1,600 error-corrected logical qubits in 2028 and on the order of 40,000 to 80,000 logical qubits by 2030 as error correction improves. CEO Peter Chapman likened the 2028 system to a distributed quantum supercomputer enabled by modular photonic networking between ion trap chips. The company expects to offer this interconnected commercial system by 2028, aiming for enterprise-grade error rates about 10 to the negative 7th power per logical operation by that time. By 2030, IonQ anticipates pushing logical error rates below 10 to the negative 12th power, suitable for high-stakes uses in secure communications and defense. IonQ is proclaiming the pieces needed for a cryptanalysis worthy quantum computer will be in hand by end of this decade. Execution risk is enormous. Scaling from today's 50 to 100 qubit prototypes to 10,000 plus qubits in just 2 to 3 years is unprecedented. IonQ counting on newly acquired tech, Oxford's chip traps, photonic links to work seamlessly at scale. Integrating 2 chips into one system by 2028 means solving daunting engineering problems in packaging, crosstalk calibration, and quantum networking. Any snag lower yield in 2-dimensional traps, difficulties getting photons to reliably entangle distant ion qubits could delay schedule significantly. IonQ's plan is by their own admission forward-looking and subject to change. Number 4. Neutral atom qubits, the dark horse. Atoms with balanced protons and electrons cooled near absolute zero. Quera, atom computing Pascal. These systems enable precise quantum control. Major technology companies investing in this approach to realize practical quantum technologies. Harvard MIT researchers demonstrated in November 2025, using Nature published November 10, 2025, a fault-tolerant neutral atom architecture for universal quantum computation. The team utilized reconfigurable arrays of up to 448 neutral atoms to implement key elements of universal fault-tolerant quantum processing architecture. Experimentally explored underlying working mechanisms. Associate Professor Tapio Simula from Swinburne University of Technology explains what neutral atoms are. A typical cold atom experiment takes a small cloud of neutral atoms millions of times thinner than air and levitates it inside a vacuum chamber using optics and magnetic fields. Then laser beams are fired at the atoms to counterintuitively cool the atoms incredibly close to absolute zero. At this point, they can no longer be described using classical Newtonian physics. From here, the laws of quantum mechanics open a world of new opportunities, with experimentalists using these ultra-cold neutral atom platforms to study fundamental laws of physics. Neutral atoms, used for building game-changing technologies including world's most accurate atomic clocks, ultra-sensitive quantum sensors, and state-of-the-art quantum computers. Atoms are manipulated using optical or microwave pulses. Offers long coherence times, scaling in 2-dimensional or even 3-dimensional configurations, and fair connectivities by long-range interactions called Rydberg states. Main challenges include further improvement of 2-qubit gate fidelities and gate operation speeds. Quera demonstrated sustained rounds of error correction on neutral atom quantum processor in June 2025. System applied surface code error correction over multiple cycles used machine learning to decode errors, executed logic gates and teleportation protocols while managing atom loss. Processor used flexible grids of up to 448 individual atoms to build and test essential parts of quantum computer, designed to correct its own errors. Researchers used machine learning-based decoder optimized to handle atom loss common problem in neutral atom setups. They leveraged Supercheck's products of multiple stabilizers that remain valid even when individual stabilizers fail due to atom loss. Setup allowed system to apply 3 or more cycles of error correction continuously without resetting entire system between rounds requirement for long-term quantum computations. Atom Computing announced partnership with Microsoft to deliver integrated quantum machine to select customers by 2025. System offered both via Azure Cloud and as on-premises hardware. Will provide reliable logical qubits on commercial quantum machine, aiming to empower early real-world applications in chemistry materials, science. Will be one of first commercial quantum computers delivered with error-corrected logical qubits, targeting on order of about 50 logical qubits initially. Atom's partnership suggests small error-corrected quantum machines will soon be in real users' hands. Atom computing made headlines late 2023, announcing 1,225 site optical atom array populated with 1,180 physical qubits. First universal quantum platform to surpass 1,000 qubits. Dramatic leap from about 100 qubit first generation system to over 1,000 qubits in one generation showcases inherent scalability of neutral atom approach. Atoms' qubits encoded in nuclear spin states of neutral atoms yields exceptionally long coherence times on order of about 40 seconds. Atom Computing White Paper published 2025 states each new generation of neutral atom quantum platform expected to achieve roughly order of magnitude 10 times increase in qubit count. Following trajectory, Atom's next generation projected to expand from about 1,000 qubits into greater than 10,000 physical qubit range, which company anticipates will yield over 100 error-corrected logical qubits on that system. Pascal France outlined plan for 10,000 neutral atom qubits by 2026, indicating Atom will not be alone in pushing this modality. China's first atomic quantum computer, Hanyuan No. 1, entered commercial use with more than 40 million yuan in orders, including sales to China Mobile Subsidiary and Pakistan, according to Hubei Daily, published November 2, 2025. System developed by Chinese Academy of Sciences Innovation Academy for Precision Measurement Science and Technology, with support from Hubei's Pioneer Program. Uses cold atoms as qubits, operates at room temperature to reduce energy and maintenance costs. Project built full domestic supply chain through province's Optics Valley cluster, developing National Quantum Computing Center to expand industrial applications in finance, logistics, materials, research. More than 50 universities and companies joined project to begin exploring quantum applications. Project team. Constructing China's first neutral atom quantum computing power center designed to host clusters of machines providing continuous 24-hour computing services. Christopher Monroe, expert on ion quantum computing at Duke University and co-founder of IonQ, says neutral atom systems still look a little like physics experiments. He's hoping neutral atom companies will show an honest-to-God system that executes an algorithm. Atom-based quantum computing must overcome several challenges, such as perfecting ways to replace atoms that fall out of grid and speeding up readout of atoms. States. Must prevent scheme's great strength ability to move atoms from becoming Achilles' heel. To avoid heating atoms can move no faster than 1 meter per second speed of slow walk. That could limit atom-based quantum computers to running thousands of times slower than superconducting machines. Mikhail Lukin from Harvard notes atom-based machines can make up time by avoiding some computational steps, for example, painstaking lattice surgery needed for other approaches. If you do lattice surgery, you have to check for errors very much more often. Denise Ruffner, commercial consultant who worked at IBM and Atom Computing, says, at moment investors care more about number and quality of qubits than speed. Yes, neutral atoms can be slow, but in many senses, nobody cares. Number 5, photonic qubits. Room temperature quantum computing. Light as qubits. Xanadu psi-quantum. Quandela QX quantum. Photonic systems use single photons particles of light as qubits. Manipulating them involves beam splitters, phase shifters, detectors. Major advantage operates at room temperature, unlike most other technologies. Photons travel fast, less susceptible to decoherence. However, reliably generating and detecting single photons remains a technical challenge. Using technique to build scalable quantum gates is still difficult. Xanadu unveiled Aurora in January 2025, published in Nature, January 22, 2025, world's first scalable connected photonic quantum computer prototype. Uses modular design with 35 photonic chips, demonstrating complete integrated systems comprising all basic functionalities for universal and fault-tolerant operation. Combines all primitive components as discrete, scalable rack-deployed modules, networked over fiber optic interconnects, including 84 squeezers and 36 photon number, resolving detectors, furnishing 12 physical qubit modes at each clock cycle. Aurora synthesized cluster state entangled across separate chips with 86.4 billion modes, demonstrated capability of implementing foliated distance 2 repetition code. System built as sub-performant scale model. Each box, or quantum server rack, added gross processing power. Team suggests thousands of racks could be tied together via fiber cables, creating massive quantum computer with massive processing abilities. Researchers made entire system photon-based, eliminating need to connect photon-based parts with traditional electron-based parts. Prototype network of 4 server racks using 84 squeezers resulted in computer with 12 physical qubits. PsiQuantum, since founding in 2016 in Palo Alto, California, raised investor funding of more than $700 million, along with significant government support in the United States and Australia to build photonic quantum computer with million qubits. Australian government announced $620 million financial package for PsiQuantum to build world's first utility-scale fault-tolerant quantum computer in Brisbane, April 29, 2024. PsiQuantum recognizes its photonics architecture will require large-scale infrastructure. Announced plans to build 2 hyperscale quantum compute centers in Brisbane, Australia, and Chicago, USA, published June 2025 Optica. PsiQuantum published Nature, February 26, 2025, titled A Manufacturable Platform for Photonic Quantum Computing. Introduced manufacturable platform for quantum computing with photons. Benchmarked set of monolithically integrated silicon photonics-based modules to generate, manipulate, network, and detect heralded photonic qubits. Demonstrated dual-rail photonic qubits with 99.98% plus or minus 0.01% state preparation and measurement fidelity. Pong-O-Mandel quantum interference between independent photon sources with 99.50% plus or minus 0.25% visibility. 2-qubit fusion with 99.22% plus or minus 0.12% fidelity. Chip-to-chip qubit interconnect with 99.72% plus or minus 0.04%. Fidelity conditional on photon detection, not accounting for loss. Study published July 2025 on ARXiv proposes detailed experimentally grounded blueprint for building scalable fault-tolerant photonic quantum computer using deterministic quantum dot emitters. Design integrates time-bin encoded photons, adaptive fusion gates low-depth architecture reducing optical complexity, enabling real-time error correction. Simulations show system meets key fault tolerance thresholds under realistic noise conditions, though achieving necessary performance benchmarks in quantum dot hardware remains central challenge. Research conducted by scientists from University of Copenhagen Sparrow Quantum University of Bristol addresses long-standing limitations in photonic quantum computing. Quandela delivered Lucy 12-qubit photonic quantum computer to CEA's Tres Grand Centre de Calcul under EuroQCS France Consortium, led by GENSI, procured by EuroHPC joint undertaking, October 23, 2025. Lucy, assembled entirely within EU with 80% European-sourced components, will be coupled to Joliot-Curie supercomputer to enable hybrid, high-performance, and quantum computing for applications in optimization chemistry machine learning. System enters full operation early 2026, with early remote access and training programs already available to prepare European researchers and companies. Quix Quantum secured €15 million in Series A funding, July 10, 2025, to deliver world's first single photon-based universal quantum computer in 2026. With funding, Quix Quantum will deliver first-generation universal photonic quantum computer designed to implement universal gate set, enabling any quantum operation. Milestone introduces universality, accelerating Quix Quantum toward delivering large-scale fault-tolerant quantum computers. Next-generation system planned for 2027 will focus on implementing error correction, crucial step towards fault-tolerant systems capable of transforming industries such as chemical engineering, drug development, fraud detection, advanced manufacturing. University of Vienna researchers published Nature Photonics, June 2025, showing small-scale photonic quantum computers can outperform classical systems in specific machine learning tasks. Used quantum-enhanced algorithm on photonic circuit to classify data more accurately than conventional methods. Experiment highlights potential energy efficiency advantages of photonic quantum platforms which could help address rising energy demands of machine learning. Philip Walther, lead researcher, said, "For specific tasks, algorithm commits fewer errors than classical counterpart. Implies existing quantum computers can show good performances without necessarily going beyond state-of-the-art technology." Number 6, quantum annealers, the optimization specialists, D-Wave. These machines don't perform universal quantum computation. They're designed specifically for optimization problems. Exploit quantum tunneling analog of sending ball through solid wall with finite probability, something that can't be done classically. D-Wave's systems currently most commercially developed quantum devices operating with thousands of qubits. Applicability, limited to specific types of problems, cannot provide universal computational power of other quantum technologies. D-Wave published landmark paper in Science, March 12, 2025, titled Beyond Classical Computation in Quantum Simulation. Research shows D-Wave annealing quantum computer performs magnetic material simulation in minutes that would take nearly 1 million years and more than world's annual electricity consumption to solve using classical supercomputer built with GPU clusters. D-Wave Advantage 2, annealing quantum computer prototype used in supremacy achievement testament to system's remarkable performance capabilities. Company claims achievement world's first and only demonstration of quantum computational supremacy on useful real-world problem. Mohammed Amin, chief scientist at D-Wave, said this significant milestone made possible through over 25 years of research and hardware development at D-Wave, 2 years of collaboration across 11 institutions, worldwide, more than 100,000 GPU and CPU hours of simulation on one of the world's fastest supercomputers, as well as computing clusters in collaborating institutions. Besides realizing Richard Feynman's vision of simulating nature on quantum computer, this research could open new frontiers for scientific discovery and quantum application development. Results shown in beyond classical computation and quantum simulation, enabled by D-Wave's previous scientific milestones published in Nature Physics 2022 and Nature 2023, which theoretically and experimentally showed quantum annealing provides quantum speedup in complex optimization problems. Scientific advancements led to development of Advantage 2 prototype's fast anneal feature, which played an essential role in performing precise quantum calculations needed to demonstrate quantum computational supremacy. Advantage 2 prototype provides substantial performance improvements from previous generation. Advantage systems including increased qubit coherence, connectivity, energy scale, enabling higher quality solutions to larger, more complex problems. D-Wave now has Advantage 2, processor 4 times larger than prototype used in work. Extended simulations from hundreds of qubits to thousands of qubits significantly larger than those described in paper. However, critics argue properly, configured classical simulations can reproduce or surpass quantum annealer performance in some cases. Competing research from EPFL, Flatiron Institute, shows time-dependent variational Monte Carlo and belief propagation offer alternative paths to solving these problems efficiently. Joseph Tyndall, quantum computer scientist at Flatiron Institute in New York City, developed a competing classical approach using belief propagation algorithm widely used in artificial intelligence. Their method, repurposed 40-year-old technique, produced more accurate results than quantum annealer in certain cases, involving 2- and 3-dimensional systems, according to Science News. Wall Street Journal noted, while experiment demonstrated performance gap favoring D-Wave's hardware, skeptics argued problem was carefully chosen to highlight quantum advantages. Critics observed advances in classical algorithms might soon close benchmark gap, suggesting D-Wave's claimed supremacy may be limited to narrow, contrived applications, rather than broad real-world problems. Independent investment research firm Carisdale Capital argued April 2025 that D-Wave's market valuation disconnected from stagnating revenue and lack of broad commercial adoption, highlighting concerns over significant share dilution questioning company's path to profitability. D-Wave announced 2021 next-generation system that became Advantage 2 with delivery expected late 2024 or early 2025. Advantage architecture expected to increase total number of qubits to over 7,000, switched to Zephyr graph topology, increasing per qubit connections to 20. As of July 17, 2025, manufacturer claimed 4,400 plus qubit system generally available. D-Wave does not implement generic universal quantum computer. Instead, computers implement specialized quantum annealing. D-Wave operates from locations in Palo Alto, California, and Burnaby, British Columbia. Founded 1999 by Haig Ferris, Geordie Rose, Bob Wiens, Alexandra Zagoskin. Company name refers to their first qubit designs, which used D-Wave superconductors. Early customers include Lockheed Martin, University of Southern California, Google, NASA Los Alamos National Laboratory. First commercially produced D-Wave processor, programmable superconducting integrated circuit with up to 128 pairwise coupled superconducting flux qubits. 128 qubit processor superseded by 512 qubit processor in 2013. Processor designed to implement special purpose, quantum annealing, opposed to being operated as universal gate model quantum computer. Underlying ideas for D-Wave approach arose from experimental results in condensed matter physics, particular work on quantum annealing in magnets performed by Gabriel Epley, Thomas Felix Rosenbaum collaborators, who had been checking advantages proposed by Bikas Chakrabarty and colleagues of annealing in presence of quantum fluctuations. D-Wave made strategic decisions early, recognizing annealing quantum computing would be more robust against errors and noise, have simpler engineering requirements than gate model approaches. Company recognized developing large-scale quantum computing technology would require building superconducting devices in production semiconductor fabrication facilities rather than research labs. Basic components of superconducting integrated circuits supporting quantum computation, such as Josephson junctions, have existed for decades. These components, developed in research and academic labs, limited ability to scale. Making use of production-scale semiconductor facilities leverages decades of research and development, hundreds of billions of dollars invested by semiconductor industry. Strategy enabled annealing quantum computing to be brought to market quickly at scale rather than having to invent new manufacturing techniques from scratch. Number 7, silicon quantum dot qubits, the semiconductor play. Dirac, quantum motion, Intel semicon. These use quantum dots, nanoscale semiconductor structures that confine and manipulate single electrons. Silicon quantum dots compatible with existing semiconductor industry manufacturing processes, making them promising for universal quantum computers. Long coherence times up to 0.5 seconds. Single qubit gate fidelities exceeding 99.95%. 2 qubit gate fidelities surpassing fault-tolerant threshold. Dirac UNSW, Sydney nanotech startup, teamed up with European Nanoelectronics Institute, Inter-University Microelectronics Center, IMECO. Together, demonstrated chips work just as reliably, coming off semiconductor chip fabrication line as in experimental conditions of research lab at UNSW. UNSW engineering professor Andrew Dzurak, founder and CEO of Dirac, said up until now it hadn't been proven processors, lab-based fidelity, meaning accuracy in quantum computing world, could be translated to manufacturing setting. Now it's clear Dirac's chips fully compatible with manufacturing processes that have been around for decades. Paper published September 24, 2025 in Nature, Teams report Dirac. Designed IMEC fabricated devices, achieved over 99% fidelity in operations involving 2 quantum bits or qubits. Achieving utility scale in quantum computing hinges on finding commercially viable way to produce high fidelity quantum bits at scale. Dirac's collaboration with IMEC makes clear silicon-based quantum computers can be built by leveraging mature semiconductor industry, opening cost-effective pathway to chips containing millions of qubits while still maximizing fidelity. Silicon emerging as frontrunner among materials being explored for quantum computers can pack millions of qubits onto single chip work seamlessly with today's trillion-dollar microchip industry making use of methods that put billions of transistors onto modern computer chips. Dirac previously shown qubits fabricated in an academic laboratory can achieve high fidelity when performing 2 qubit logic gates, basic building block of future quantum computers. Latest achievement clears way for development of fully fault-tolerant functional quantum computer, more cost-effective than any other qubit platform. Christiane de Greve, fellow and program director for quantum computing at IMEC, said for first time, silicon MOS-based quantum dot spin qubit devices realized with industrial manufacturing techniques, perform as well as academic hero devices. Shows IMEC's 300mm process flow for MOS-based quantum dot structures, enables low-noise qubit environment resulting in high fidelity values for set of critical qubit operations. Methods used and insights gained show there is further room for fidelity improvement, as higher fidelities can be achieved through even further isotopic enrichment of silicon channel layer. Quantum Motion, London-based startup, created world's first silicon-based quantum computer manufactured, using same transistor technology found in nearly all modern digital electronics, September 2025. Machine built using complementary metal oxide, semiconductor, CMOS chip fabrication process, same used to create chips for devices like smartphones, laptops, digital cameras. CMOS technology widely used because it produces chips that don't draw power when idle. Integration in quantum computer paves way for broad adoption, less expensive manufacturing processes. James Pals-Dimick, chief executive of Quantum Motion, said this is quantum computing's silicon moment. Today's announcement demonstrates you can build robust functional quantum computer using world's most scalable technology with ability to be mass-produced. System represents first silicon spin qubit computer developed under auspices of UK National Quantum Computing Centre's Quantum Computing Testbed Program initiative to build 7 prototype quantum computers using differing technologies test their viability. Research undertaken by Quantum Motion in conjunction with University College London to create more fault-tolerant quantum systems demonstrated 98% accuracy in 2 qubit gates, fundamental building block of quantum circuit. World-leading mark in qubits, fabricated in natural silicon on 300mm wafer scale, same material used in new computer. Fault tolerance, critical to quantum computing because qubits notoriously fragile, error-prone. Instability due to a property called decoherence. Superposition ability for qubit to exist in multiple states at once, an entanglement ability of two or more qubits to be connected to one another, share same state across distances both necessary for quantum computing advantages. Changes in temperature, electromagnetic interference. Other environmental factors can distort or collapse those properties, leading to inaccurate results. Intel's tunnel falls. 12-qubit silicon chip fabricated on 300mm wafers in D1 fabrication facility in Hillsboro, Oregon, marks next step toward building full-stack commercial quantum computing system available to quantum research and academic community which lacks high-volume manufacturing fabrication machinery. Jim Clark, director of Quantum Lab at Intel, said Tunnel Falls is Intel's most advanced silicon spin qubit chip to date, draws upon company's decades of transistor design and manufacturing expertise. Together with access to Intel's quantum software development kit, access to Tunnel Falls constitutes tangible effort to democratize quantum computing research. Utilizing advanced CMOS fabrication lines allows Intel to use innovative process control techniques for better yield and performance. Intel claims Tunnel Falls. 12-qubit device reaches 95% yield rate at wafer level with voltage uniformity, similar to CMOS logic process. Researchers at Quantum Motion demonstrated integration of 1,024 independent silicon quantum dots with on-chip digital and analog electronics, all operating at extremely low temperatures. January 23, 2025, published Nature Electronics. Used radio frequency reflectometry for rapid characterization, achieving high signal-to-noise ratio. Researchers developed new tools that can be used to extract information about performance of quantum dots, assess their potential for integration in quantum technologies. Tools could be used to assess other types of quantum dot-based systems, including systems with coupled quantum dots, basis of existing semiconductor-based quantum computers. Researchers observed cryogenic parameters of silicon quantum dots can be predicted from room temperature behavior. Finding could have interesting implications for future development of quantum technologies, as it could help reduce time and resources required for testing quantum devices. Silicon quantum dots, also called artificial atoms. Basic structure of silicon spin qubits. Tiny structures can trap and control individual electrons, allowing researchers to define various types of spin qubits. Single electron dots can be manipulated with alternating current magnetic fields, while two electron systems and double dots use exchange interactions to define qubits, such as singlet, triplet qubits, to construct various 2-qubit gates, including swap gates, controlled phase, gates controlled not gates. Gate-defined quantum dots built using electric fields to trap electrons with fabrication, relying on substrates like silicon, silicon-germanium heterostructures, or silicon metal oxide semiconductor structures. Donor-based quantum dots, dopant potential binds. Electrons around nuclei, hyperfine interaction links electron spins to respective nuclear spins, providing excellent physical degrees of freedom for encoding qubits. Both share common technologies. Spin coherence times for both quantum dots significantly prolonged using isotopically purified materials. Qubit initialization, readout achieved through spin to charge conversion processes such as spin-selective tunneling, polyspin blockade. Single qubit gates manipulated using electron spin resonance or electric dipole spin resonance techniques. 2-qubit gates implemented by utilizing exchange interaction between qubits. Realizing long-distance coupling of spin qubits crucial for increasing number of qubits enabling distributed quantum computing architectures. Circuit quantum electrodynamics using microwave photons and superconducting resonators making this possible. Strong spin photon coupling demonstrated using hybrid techniques like synthetic spin orbit interactions provided by micromagnets. Silicon spin qubits compatible with existing semiconductor industry manufacturing processes, making them promising for universal quantum computers. 7 paths, 7 architectures, all chasing same impossible target. Fault-tolerant quantum computer, capable of solving problems. Classical computers cannot touch. Superconducting qubits have commercialization advantage, IBM Google scaling to thousands of qubits, but need extreme cold. Topological qubits promise hardware-level error correction. Microsoft betting everything, still proving Majorana zero modes are real. Trapped ions offer precision. Quantinuum ion Q hitting 99.9% fidelity. Slow. Hard to scale. Neutral atoms offer long coherence times, room to scale in 3 dimensions. Quira, atom. Computing racing to 10,000 qubits. Still look like physics experiments. Photonic qubits run at room temperature. Xanadu, psi-quantum building million qubit machines. Generating single photons remains hard. Quantum annulars solve optimization today. D-Wave, claiming supremacy on magnetic materials, not to universal computers. Silicon quantum dots leverage trillion-dollar semiconductor industry. Dirac quantum motion Intel proving 99% fidelity in foundries. Path to millions of qubits. Still early. Each technology faces bottlenecks. Superconducting qubits fight noise. Topological qubits fight skepticism. Trapped ions fight speed. Neutral atoms fight heating. Photonic qubits fight loss. Quantum annealers fight scope. Silicon qubits fight disorder. No clear winner yet. Maybe there won't be one winner. Maybe finance runs on trapped ions, drug discovery on photonics, logistics on annulars, material simulation on superconducting, each optimized for different problems. What changed in 2025? Error correction. Google's Willow chip in December 2024 showed reducing errors as you add qubits. Microsoft's Majorana, one in February 2025, showed hardware-protected qubits. Quantinuum's Helios in November 2025 demonstrated error correction on the fly with 99.9% fidelity. Harvard MIT's neutral atom work in November 2025 showed fault tolerance with 448 atoms. Dirac and IMEC in September 2025 proved silicon qubits hit 99% fidelity in industrial foundries, not just labs. These aren't incremental. These are thresholds. Crossing from noisy intermediate-scale quantum to fault-tolerant quantum computing. Investment following. McKinsey projects 5,000 operational quantum computers by 2030. Hardware and software required to tackle most complex problems not expected until 2035 or later. Quantum computing companies generated $650 to $750 million revenue in 2024. Over $1 billion expected in 2025. Revenue surge comes from continuous growth and deployment of quantum hardware across private industry defense sector. Value shift coming. Quantum computing startups moving from hardware towards software next 5 to 10 years. Australia's $620 million commitment to PsiQuantum. Illinois, $500 million quantum park. Singapore $222 million investment. Japan, $7.4 billion announced early 2025. This isn't research money, this is deployment money. Governments betting on quantum advantage arriving within decade. Race for a cryptographically relevant quantum computer heating up. IonQ targeting 20,000 qubits by 2028, claiming 1,600 logical qubits. Enough to threaten current encryption standards. Post-quantum cryptography becoming urgent. But here's what nobody talks about. 7 different paths means 7 different failure modes. Superconducting qubits could hit wall at 10,000 qubits, unable to maintain coherence. Topological qubits could remain lab curiosities, never scaling beyond proof of concept. Trapped ions could stay too slow for practical computation. Neutral atoms could never solve heating problem during shuttling. Photonic qubits could drown in optical loss before reaching useful scale. Quantum annulars could remain niche, unable to expand beyond optimization. Silicon qubits could face insurmountable disorder in large arrays, or all 7 could work. Multiple platforms coexisting, serving different markets. Hybrid systems combining approaches. Superconducting qubits for fast gates. Trapped ions for long coherence. Photonic interconnects for networking. Classical computers handling error correction. Quantum annealers pre-processing optimization problems. Reality probably messier than any roadmap suggests. One thing's certain. 2025 marked shift from physics demonstrations to engineering deployments, from claiming quantum supremacy on contrived problems to tackling real simulations, from lab prototypes to commercial systems, from tens of qubits to thousands, from talking about error correction to demonstrating it repeatedly, reliably. The quantum computing race isn't one race. It's 7 simultaneous sprints towards same finish line, each runner taking completely different route. Some will stumble, some will pivot, some will discover shortcuts nobody predicted. The winner might be technology that doesn't exist yet. Or there might not be winner at all, just different tools for different jobs. What we know for sure, quantum mechanics works, superposition, entanglement, interference. These aren't theories anymore. They're engineered, controlled, deployed. Question isn't whether quantum computers will transform computing. Question is, which architecture gets there first and what problems they solve that matter. In Leuven, Belgium, September 2025, researchers pulled silicon quantum dot device off 300mm production wafer. Same wafer that makes chips for your phone. Tested it. 99.1% fidelity on 2-qubit gate, not in specialized lab. In commercial foundry, that chip cost fraction of dilution refrigerator housing, superconducting quantum computer, can be manufactured by thousands. integrated with classical electronics on same die, operates at 1 Kelvin instead of 15 millikelvin, still cold, but 300 times warmer than competing approaches. That's the kind of detail that changes everything. Not the qubit count, not the quantum volume, the manufacturing reality, the engineering economics, the path from one device to 1 million devices. Every quantum computer type has a moment like that buried in specifications. Photonic systems running at room temperature, neutral atoms with 40-second coherence times, trapped ions with all-to-all connectivity, topological qubits with hardware-protected states, quantum annealers with 4,000 qubits today, not tomorrow. Each advantage comes with trade-off. Each trade-off might be solvable or might be fundamental. That's what 2025 taught us. The trade-offs are real. The advantages are real. The question is, which trade-offs matter most for which applications and which advantages can be preserved while scaling? Nobody's celebrating victory yet. IBM targeting 2033 for quantum-centric supercomputer. Microsoft betting on million-qubit chip timeline measured in years, not decades. Quantinuum planning. Apollo for 2029 with full fault tolerance. IonQ claiming 2028 for a cryptographically relevant system. Atom computing predicting 10,000 qubits by next generation. PsiQuantum building million-qubit photonic systems in Brisbane and Chicago. D-Wave already at 4,000 qubits claiming supremacy on materials simulation. Dirac proving silicon works in foundries today. 7 different timelines, 7 different definitions of success, 7 different ways to build a machine that exploits quantum mechanics for computation. The race isn't over, it's accelerating. And the finish line keeps moving as researchers discover what's actually possible versus what seemed possible 5 years ago. Final number, 100 years since quantum mechanics was formalized, 1925 to 2025. It took a century to go from understanding wave-particle duality to trapping individual atoms in laser tweezers and performing logic gates on them with 99.9% accuracy. It took a century to go from Heisenberg uncertainty principle to engineering systems that exploit uncertainty for computational advantage. It took a century to go from Schrödinger's equation to building machines with thousands of qubits entangled simultaneously. Next century won't take a century. 10 years from now, quantum computers will either be running drug discovery pipelines and optimizing supply chains and breaking encryption, or they'll be cautionary tale about hype outrunning capability. 2025 was the year we found out which trajectory we're on. The engineering works, the physics is sound, the money is committed, the facilities are being built. The question isn't if anymore. The question is when and which approach, and whether the problems we solve actually matter or just make good press releases. 7 types of quantum computers. 7 ways to harness superposition. Entanglement, interference, decoherence, tunneling topology. 7 paths from classical computing to something fundamentally different. The winner won't be determined by elegance of physics or beauty of theory. Winner will be determined by which architecture scales cost effectively to millions of qubits, while maintaining fault tolerance and solving problems people actually pay to solve. That's not physics question anymore. That's engineering question. Economics question. Manufacturing question. And the answer is being written right now in dilution refrigerators in Colorado, in laser labs at Harvard, in semiconductor foundries in Belgium, in photonic clean rooms in Australia, in ion trap facilities in Singapore, in annealing systems in Vancouver, in quantum dot arrays in London. 7 different answers to the same question. How do you build a machine that thinks in quantum mechanics while existing in classical world? We're about to find out.